I had a good amount of that metal under the dies. And specifically, I had enough metal under the die when I started that this distance from here to here was at least, in my case, about 2 inches. And that I arrived at that because the height of this is 2 inches. So if I could actually get away with less. I probably could have gotten away with about 1 inch, but I went ahead and took a little bit more. If I had gone with anything less than 1 inch, I would have had this condition occur. So I made sure to overshoot a little bit. Now, one thing that I will often do in my shop is I will take my very first blow with a tiny little bit under the die, because if I have overheated, if I've overheated the workpiece, I'll end up with metal squirting out. But if I only take a tiny little bit and I don't hit it real hard, I only damage or not damage or lose any material. But if I do that and I've overheated the workpiece and it doesn't look like it's overheated, but it is, if you take a big bite like that, you smack it, and if you squirt that brass out from in between, when you tip it up and work it at 90 degrees to your original forging direction, it'll often split apart. So I kind of, as a safety technique, I'll often take just a little tiny nibble, just that first bite or two. Just enough to prove to myself that the work is not too hot. If it is too hot, what I can do is take it out and just let it sit. And let it cool off, and then it's good to go. Once we get that little bulge on the end, we don't have to be quite so concerned about having that center line sort of, at work I would call it a suck-in type of defect occur. And so I can go and begin using smaller die bites, which is what I just did there. And I did that for a couple of reasons. One is I need to work the metal within the capacity of the hammer. So if I'm trying to take too big of a die bite for the machine, it's just going to take a really long time. If also I know I'm not able to work the whole piece end to end. I'm holding one end and I'm not flipping it around in the same heat. So I need to make sure that I leave a nice tapered transition between the large cross-section end that I haven't worked and the end that we're working on finishing, because I'm going to take it all down to 1 inch cross-section by the time I'm done, and I don't want to have any forging laps in there. So if I were to forge a whole bunch of it and make kind of a sharper shoulder, and then flip that around and forge it, it might fold over and I'd have to do some grinding and lose some material, or just take extra time that I don't want to do. So we're trying to use the tools in a way that's controlled to get the outcomes that we want. I had an interesting question at the break about another type of problem that can happen, happen in particular when it can happen with anything. I find this material to be particularly at risk for this problem of having the layers want to separate when they're forged in a shearing action. Here, what I'm doing right now is I'm either forging parallel to the layers and compressing them, or exactly perpendicular to the layers, and we have a bit of a tensile load going on. Neither of those is too horrible unless I get really aggressive with take a huge bite, big massive spread to the side with the layers vertical, which I'm not doing. But at a certain stage of this process, we're going to turn the square into an octagon, and when I do that, those layers are now going to be laying at 45 degrees to the plane of the dies, so they're going to have a tendency to want to shear apart. So I need to be able to counter that. The way to do that, I still have to put them up on the corner to make an octagon. There's no other way to go about doing that. But I want to minimize that shearing action. So the way I will do that is to minimize how much metal I'm deforming with any one blow of the die. So I'll take very, very short die bites and very shallow hits, and I'll make multiple passes to establish those corners, and that usually is very successful. And the other thing is that even though the final product coming out of this is going to be round, I won't make it round. I'm going to make an octagon. Well, actually, one piece will be round. It'll be an octagon that's twisted, and we're going to just twist it really tight and leave it as a twisted octagon. The other one will be twisted and flattened, but I often do make round, or product that will become round. And the way we go about doing that is we make an octagon, and we'll twist it, and then we'll just leave it as an octagon, and I'll send it back to Mike, and he'll throw it in the lathe and turn it. And you might say, well, why not forge it round? You could do that, right? You got a hammer, you make it round. And that's true, I absolutely can. However, if you don't do that right, you can make a hole. And so I can actually forge a hole into something that didn't have a hole to begin with if I don't do it properly. And I had that happen one time, and I had made a bar about so long, it was round, I cut it in half to fit in the box. It was, Mike was okay with that. As soon as I made that cut, I could see I had a hole right in the center. And I knew exactly what had happened and why it had happened. But Mike wasn't making beads out of that part, so that wasn't good for him. So we avoid that problem in this case by just leaving things as octagons. But you don't have to do that. We'll talk about that in a I feel like I'm at home. I set my cars down and give me 1 to 5 places. They're all within like this. Okay, so got one end worked down to 1 inch square. We'll flip it around in the forge and take the other end down in the same way. Oh yeah. So Dave just commented and said, it's amazing you can take that much pressure. And it does sort of seem that way. But when the bonds are done properly, you can do all kinds of stuff with this material. There are folks who've made large sculptural vessels out of not necessarily Mike's material, but material produced in the same way. So yeah, if the bonds are done correctly, and you understand how to work the material, you can do a lot with it. So you're usually at home when I'm doing a job like this, I'll have quite a few of these, and I'll have maybe 3 or 4 in my furnace at a time. And we'll be constantly going back and forth, so there's not a lot of downtime.
But he did take it out.
Okay. I was in the middle of explaining something when I stopped the forge. What was I talking about?
Holes in the middle.
Holes in the middle, right, because Bruce asked me to cover that. Thank you. So, why does that happen? So what happened in my case was I had a piece that was round, but it was bigger round than I wanted it to be by, I don't know, maybe 3/16, eighth of an inch, something like that. So what I did was I had my flat dies, and I put in a different set of stop blocks to get to the correct dimension. So let's say, you know, I had a block in here, that. And I put the workpiece in, got it hot, and I just started tapping it and rotating it. I just kept tapping and rotating and tapping and rotating. And it was coming down to the dimension that I wanted, and eventually I got to the size that I wanted. But what was happening was that because of the way that was being forged, I was applying pressure, not so much right here, which is what we would normally expect to happen, right? If I'm working a square piece, and I'm working on the square, I have the load coming straight down and sort of straight up, right? So everything, all that loading is aligned. What happened with my circumstance was I was rotating and hitting at the same time. So instead of having that load applied at the 12 o'clock and 6 o'clock position, I had load being applied more like at, say, the maybe 1 o'clock and like 8 o'clock position, something like that. But the load is actually coming down this way, so, and it's coming up this way, but my contact wasn't, so my dies are coming straight up and down, but the contact spot wasn't straight up and down. The contact was happening off center. And so instead of having load that was sort of compressing everything nicely at the center, what I ended up with was a load off center here, pushing down, and a load from the bottom die off center over here, pushing up. And what does that result in? That means that right along the center line, you have a shearing action. And that shearing action is what caused that hole to develop. So you'll find in some old reference books, old blacksmithing books where they talk about forging high carbon steels or tool steels, they would say, don't forge them round. Leave them as an octagon because of that problem. And they show illustrations of having things with holes forged into them. We've done the same thing at work on numerous occasions. There's not just with tool steels, but a lot of other steels. This can happen. This can happen. This can happen when your workpiece is on the cold side. This problem is the metal being colder is less formable, less ductile, and so the shearing activity is sort of magnified when the temperature gets colder. Certain materials are more at risk. So at work, we deal with a lot of different kinds of steels, certain stainless grades, and some of those are at much greater risk for this. So let's say you're forging some stainless and you have some 1018, and you're going to make the same size and shape out of both. Your stainless materials will be much more likely to have this happen. You have to be much more careful to avoid this than you would be with a piece of 1018. You could still have it happen with 1018, but you have a wider temperature range, which you can work safely. You can be a little more aggressive with your deformation, maybe a little bit sloppier with your control before you're going to start a problem there. So that's another aspect of control, and in the case of laminated materials, we have the extra challenge of an interface that we've created on purpose between the alternating layers, and that's going to be a potential area that could separate. So we have to be extra careful about it when we're dealing with laminated work pieces, and in my case, where I'm dealing with cross sections that are fairly small, I often end up making octagons out of 3/4 inch square bar, which is probably what we'll do today with part of this. And my dies, as I said earlier, are 4 inches wide. So I could break the corner with a 4-inch wide die bite, but if I did that, I would be displacing all of that 4-inch material, 4 inches of material all at one time, which is going to magnify the stresses at the center. If I shorten that die bite and use, a 1-inch die bite or a 1/2-inch die bite, I can accomplish the same thing. It takes a lot more strokes of the hammer, but it's less risky to the material.
Of course, not worried about a non-magnetic. Of course, not worried about magnetic transition. But what's your lower end safety range?
Okay, so Dave asked me, how do I know when to stop forging? So in this case, I'm stopping forging when the hammer stops moving the material. But if I had a bigger hammer, I could go longer at that temperature. I could go a little bit lower temperature than what I just put that back at if I were using